Okay, so today is our lesson on graphing rational functions. We have talked about rational functions a couple of times already. So the difference today is that we're going to talk about something called a slant asymptote, which is another type of asymptote, and the last type of asymptote that we're going to talk about this semester. So in order to get back into this, I would like to quickly sort of review our horizontal asymptote rules. The horizontal asymptote rules that we talked about in Module 2 were the ones that we had to just sort of memorize, right? So if you'll recall, there were 3 of them. So the first one was if the degree of the numerator was greater than the degree of the denominator, then we had no horizontal asymptote. That was the first one. Yeah. The second one was that if the degree of the numerator was equal to the degree of the denominator, that's a D, denominator, then we had an asymptote at A over B, where A and B were the leading coefficients. So this was the ratio of leading coefficients. And then the third rule was that the degree, if the degree of the numerator was smaller than the degree of the denominator, then we had an asymptote at y equals 0. And this guy should also say y equals A over B. And remember, asymptotes are always a line. So because of that, we either need to include x equals or y equals, depending on what we're talking about. Okay, so these were the rules before we had sort of just memorized them. So now that we have a few more tools in our toolkit, we're actually able to figure this out. This isn't something that we have to necessarily memorize anymore. So the end behavior of a rational function f of x, p of x over d of x will be the same as that of the quotient of p of x over d of x. So what does that mean? Well, let's take a look at this. Okay, let's look at some examples here. So let's say we're looking at f of x equals 3x squared plus 2x plus 2 divided by x squared plus 5x plus 1. All right, so in this situation, we have the same degree, right? We have the degree of 2 on the top and a degree of 2 on the bottom. So we know from our rules, right, if we were just memorizing, we would know that we would have a we would have a horizontal asymptote at y equals a over b, a and b being the leading coefficients. So we would know, right, so our horizontal asymptote rules say that we have a horizontal asymptote at y equals 3 over 1, or 3. Let's look at what our graph looks like here. So this is not going to be perfect, but the important things to note are that we have, again, our horizontal asymptote at 3 and this vertical asymptote here. And the graph looks like this. We come down, we almost touch the x-axis, and then we come back up and sort of get really, really close to this line. So again, this is y equals 3. So how does this relate to this fact that we just talked about? So our fact says that the end behavior of our rational function. So let's remind ourselves what end behavior means. End behavior is what's happening to the graph as we move off the edges of the graph, either to the right or to the left. What is happening here? So if you recall, remember end behavior, we would write it like this. So as x approaches negative infinity, right? So as our x values are going off the graph to the left, right? Negative infinity. Horizontally, we're moving to the left. Vertically, y is approaching, what are we approaching? What is this line? It's 3. So as x approaches negative infinity, y approaches 3. And as x approaches positive infinity, so as x approaches positive infinity, as we move off the graph to the right, y, what's going on here? As we move to the right, y is approaching vertically. As we move to the right horizontally, vertically, we're approaching 3 as well. So that end behavior, our fact is saying that that end behavior will be the same as that of the quotient of this division problem. So if we divide this numerator by this denominator, that quotient will be the same as the end behavior for our function. So let's look at that really quick. So quotient, that means we're going to be dividing. We can't use we have to use long division here, right? We can't use synthetic division. This denominator does not allow us to use synthetic division. Okay, so when we're dividing, what's our first step? We want to divide first term by first term, so we divide 3x squared by x squared. We're left with 3. That 3 needs to go above the like term, so that goes up here. And that's it, we're done, right? This is our whole quotient. After this, all that's going to be left is the remainder. We don't need to know anything about the remainder, we just need to know the quotient. So, if we want to find, it's not a coincidence that this is the same as our horizontal asymptote. That's what this is saying. So if we divide this numerator by this denominator, we're going to get the horizontal asymptote. The quotient of this division problem is the horizontal asymptote. So this time, let's call this function g of x, and let's look at what would happen if we had x divided by 2x squared plus 1. So this situation that we're in, we have a degree of 1 on top, a degree of 2 on the bottom, so we have a larger degree in the denominator this time. So our horizontal asymptote rules say what? Well, larger degree in the denominator than in the numerator means that we have an asymptote at y equals 0. So y equals 0. Let's draw this graph. This one's a little bit more simple than the last one. You don't have to take my word for it that it looks like this. You can totally go graph this in Desmos, and I would recommend doing so, just so that you can see for yourself what's going on. So what's up with the end behavior here? As x approaches negative infinity, y is approaching what? So as we go off the graph to the left, horizontally we're moving left, vertically we're getting really, really close to 0. As x approaches positive infinity, as we move off the graph to the right, as we move right horizontally, vertically we're getting really, really close to 0. Y is approaching 0. That lines up with our horizontal asymptote rules. Let's see if it lines up with our fact. So our fact is saying that if I divide x by 2x squared plus 1, I should get 0. So let's give it a shot. 2x squared plus 0x, remember we need that placeholder always. And we're dividing x plus 0. Again, another placeholder because we're missing that constant term. All right, so we divide first term by first term. Can I divide x by 2x squared? What's left over when I do that? Nothing, I can't divide that. I can't do that division. So this comes out to 0. So again, we have the same value that we got for our rules that we sort of memorized. We're getting it in this other way that doesn't require us to do any memorization. Great. Okay, let's look at one more example like this. All right, let's say we're looking at f of x equals 3x cubed plus 5x squared plus 2 divided by x squared plus 1. So Again, really quickly, what do our horizontal asymptote rules say? Well, we have a degree of 3 on top and a degree of 2 on the bottom, right? So our rules say, because our numerator, the degree of our numerator is larger, that we have no horizontal asymptote. So that's strange, and we don't really know how that ties into our fact. So let's check it out. Let's see what happens when I do the division. So x squared plus 0x plus 1, 3x cubed, 5x squared, 0x plus 2. All right, so let's start this division. So we get 3x cubed divided by x squared. What are we left with? 3x. All right, so that 3x goes above the like term, which we have because we have this placeholder 0, right? We always want to make sure we're lining up our like terms. We multiply what we just put up here by the divisor. So 3x times x squared is 3x cubed, right? It should match exactly what's above it. Then 3x times 0x is 0x squared. And then 3x times 1 is just 3x. So we subtract all this. Subtracting, we get 0. Subtracting, we get 5x squared. Subtracting, we get negative 3x. We bring this 2 down. We do the same thing. So we divide first term by first term. So 5x squared divided by x squared. And we get 5. We put that above the like term. And this is what we get, right? We don't have to finish. We don't have to find the remainder. We're just looking for the quotient, which we're done once we find everything up to the constant term. So what does this mean? So we didn't get a number here, and we know that we don't have a horizontal asymptote. So what does it mean that we have 3x plus 5 here? Well, let's look at the graph. So first of all, let's draw the line 3x plus 5. So 3x plus 5 has a vertical intercept of 5, and it has a slope of 3. So that's a line that kind of looks like this. Kind of steep, but not crazy steep. And what exactly does this function look like? Well, again, you can verify this in Desmos, but this function looks like this. So again, this is the line y equals 3x plus 5. And the graph is doing the same thing as what we got here, right? The graph is following this line. In this scenario, we have what we call a slant asymptote. So let's define that. So definition, an asymptote that is neither horizontal nor vertical is called a slant asymptote. So anything that is not completely vertical or completely horizontal is called a slant asymptote. So anything that is like this, like this, like this, like this. So when do we have a slant asymptote? So let's look at these different scenarios that we've talked about. And I would like for us to specifically focus on the division that we're doing. So when we divide, we've talked about this before. When we divide something of degree 2 by something of degree 2, we're sort of dividing out x values, right? So when I divide something with 2 roots by something with 2 roots, we get something with no roots. If I divide something with 1 root by something with 2 roots, then I have something that is just 0. It just has to be 0, right? We can't fit something that has more x's into something that has less x's. So in this case, we're dividing something that has 3 x's by something that has 2 x's. And what are we left with? Something that has 1 x. And something with 1 x is always a line, right? It's always linear, right? Y equals something with 1 x. Maybe it's 3x plus 5. Maybe it's negative x plus 1. So that will always be a line. So we got this 1x left over because we had 1 more x in the numerator than we had in the denominator. So, fact. Slant asymptotes occur when the degree of the numerator is exactly 1 larger than the degree of the denominator. Great, okay, and the second thing I would like for us to notice is that, remember, so we get these slant asymptotes by doing this division problem. When we do this division problem, we can either get something that has an x in it or something that doesn't have an x in it, like one of these, right? So in these cases, we have a horizontal asymptote, and in this case, we have a slant asymptote. We can't have both, right? We can't get something that has a degree of 1 and something that's just a constant term. So because of this, we cannot have both a slant asymptote and a horizontal asymptote. We cannot have both. I'd like for us to look at this chart in the lab manual. Okay. We are going to skip number 1, but I would like for us to look at number 2 and 3. Number 2 what is our domain here? So remember, when we're looking for the domain of a rational function, we want to look for where the denominator is not 0. So we want x minus 2 to not be 0. Right? So x cannot be 2. When does this occur? When we have either a whole or a vertical asymptote, right? Those are our two interrupters in our domain for rational functions. So is this a whole? Is x equals 2 a whole? It's not, right? If x equals 2 was a whole, we would need to have another x minus 2 factor in the numerator. But we don't have that, so we have no wholes. Not applicable. Vertical asymptotes. Do we have any vertical asymptotes? Well, we know that if this x equals 2 is not a whole, then it has to be a vertical asymptote. X equals 2. And remember, asymptotes are not just numbers, they're lines, and we have to include their whole equation. So we are not just going to say 2, but we are going to say x equals 2. All right, horizontal intercept. So this is where our y value is 0. And remember, vertical asymptotes come from factors of the denominator that are not also factors of the numerator. Okay, moving on to horizontal intercept. So these are where y equals 0. So when is this going to be equal to 0? Well, whenever a fraction would be equal to 0, which is when the numerator is equal to 0 only. So when is this numerator equal to 0? Well, it's equal to 0 at -5 and 4. So we have the horizontal intercepts, -5, 0, and 4, 0. And I found those by setting each of these factors equal to 0. All right, vertical intercept. So this is where we have x equal to 0. And that's very, very simple. We just plug in 0 for x. I know this is really small, but maybe you could do the work on your own pages. So we would just plug in 0 here. So we would have 3 times 0 plus 5, which is just 5, times 0 minus 4, which is just -4, divided by 0 minus 2, which is -2. We end up getting 30. All right, horizontal asymptote. So this is the juicy stuff for the day. So we've been talking about this a lot. We want to figure out where we have a horizontal asymptote. So we want to divide the numerator by the denominator. That's not going to be super easy the way that it is right now, but it shouldn't be terribly hard. So this time we're going to have to do a little bit of work before we can do this division because it's factored. So we need to multiply, we need to FOIL everything out. So 3 times x plus 5 times x minus 4. We can FOIL these guys, we get x squared. We have plus 5x minus 4x, so plus x minus 20. So we're going to get 3x squared plus 3x minus 60. All right. And we want to divide that by x minus 2. So we do first term by first term. We're left with 3x. We put that above the like term. We multiply 3x by x. 3x squared 3x by negative 2 minus 6x. We get 0 plus 9x. Right, remember we're subtracting, so this is plus 9x. We can bring this guy down if we want. Now we divide first term by first term again. 9x divided by x just gives me 9. Now that I've found my constant term, this is it. This is my whole quotient. So this tells me that I have an asymptote at y equals 3x plus 9. Now, is this a horizontal asymptote or a slant asymptote? It's a slant because it's not a constant. Right? Horizontal asymptotes are like y equals 3 or y equals negative 2 or y equals 17. But here we have an x term, so we have a slant asymptote. So this is a slant asymptote. If we have a slant asymptote, it means we don't have a horizontal asymptote. So none there. And our slant asymptote is y equals 3x plus 9. It asks you to state whether we have an oblique asymptote. We're not going to talk about that. An oblique asymptote is essentially like a slant asymptote with a higher degree, but we're not going to talk about those this semester. Okay, let's look at number 2 here. So number 2 asks for domain. Again, we want to set the denominator not equal to 0, and that tells us that x is not negative 3. Now we need to figure out whether we have a whole or a vertical asymptote here. We can't really tell because we can't see exactly what the factors are of the numerator. So let's factor that numerator really quickly. We want to pull everything that we can out of these two terms. So what do we have in common here? Well, definitely we can pull out a 2. That leaves us with x squared minus 9. What do we recognize this as? Hopefully we recognize it as a difference of squares. So we have x plus 3 and x minus 3. So this guy is a repeat, right? We have a repeated factor in the numerator and the denominator. So what does that mean? It means we have a whole at x equals negative 3. How do we find the y value of the whole? Well, remember, we want to cancel out those like factors, those repeated factors, and then plug it into what's left. So we cancel these guys. We're left with 2 times x minus 3, right? There's nothing left on the bottom. It's over 1. So we plug in negative 3 here. So we get 2 times negative 3 minus 3 is negative 6, and we get negative 12. So our whole occurs at negative 3, negative 12. Awesome. So what about vertical asymptotes? Do we have a vertical asymptote at x equals negative 3? No, we don't, because we just found a whole at negative 3, right? If we have a whole there, we can't also have a vertical asymptote there. And remember, vertical asymptotes come from factors of just the denominator, right? If it's also a factor of the numerator, which x plus 3 is here, then it's not a vertical asymptote. So we have no vertical asymptote here. All right, horizontal intercept. So this time again, we want to figure out where this function is equal to 0. That's going to be where the numerator is equal to 0, so where this guy is equal to 0, but not the denominator, right? Horizontal intercepts come from where the numerator is equal to 0, but not the denominator. So we will not have a horizontal intercept at -3, even though this is a factor, because it's also a factor of the denominator. We will have a horizontal intercept at +3 because of this factor. So since x minus 3 equals 0, then x equals 3, and we have a horizontal intercept at 3, 0. All right, a vertical intercept. So again, this happens when we plug in 0 for x. Here, we just get 2 times 0 squared minus 18 divided by 0 plus 3. So that just comes out to 2 times 0 squared is all 0, so we get -18 divided by 3, or just -6. I know this is small, 0, -6. All right, horizontal asymptote or slant asymptote. Let's see what we're going to have. If we go ahead and look at it, remember our fact told us that if we have a degree of 1 larger on the top than on the bottom, then we're going to have a slant asymptote. So we do know that it's going to be a slant, but we need to find it. So let's go ahead and do that division anyway. So we're starting out with x plus 3. We're dividing 2x squared plus what? 0x, can't forget it, minus 18. All right, we divide first term by first term. We get what? 2x. We put that above our like term. We multiply 2x times x. We multiply 2x times 3. And we subtract. We get 0 here. And we get -6x here. We divide first term by first term again. -6x divided by x is -6. We get -6. That's our answer. So we have a slant asymptote at 2x minus 6, not a horizontal asymptote. Let's look at this problem here. So we have f of x. We're asked to find the relevant information and to sketch a graph. So what is all the relevant information? So we want to find all of the asymptotes, all of the holes, all of the intercepts, all that stuff. So what have we got? Let's look for maybe intercepts first. So x-intercept. All right, where do x-intercepts come from? They come from the numerator and not the denominator, so anything that is a root of the numerator and not the denominator. So what is that here? Well, we have a factor of x plus 3 and a factor of x plus 1. Neither of those are also factors of the denominator, so we know that we have x equals -3 and -1. So we have x-intercepts at -3, 0 and -1, 0. All right, what about y-intercepts? So this is where x is 0, and all we have to do is plug in 0 for x. Super easy. So we end up with 3 times 1 divided by 2, or 9/2, also known as 4.5. Do we have any holes here? No, we don't, because a hole would come from having a repeat factor on the top and on the bottom. We don't have a repeat factor here, so we have no holes. No hole. All right, now all that's left is asymptotes. So let's look for a vertical asymptote first. Where do those come from? Well, we know that they're going to interrupt our domain, so we know it's going to come from the denominator. So x plus 2 equals 0. That means we have a vertical asymptote at x equals -2. Lastly, horizontal asymptote. All right, so this is the tricky one. So with this one, we need to do the division, which means that we need to FOIL this out and figure out what our numerator looks like. So we FOIL out these two guys, the 3's along for the ride. We get x squared plus 3x plus 1x, so plus 4x plus 3. We distribute that 3 to all of those terms. We get 3x squared plus 12x plus 9. So this is our numerator, our full numerator, and we want to divide it by x plus 2. I'm running out of space here. All right, so we divide first term by first term. 3x squared divided by x is just 3x. We put that above 12x, the like term. We multiply 3x by x plus 2. We get 3x squared plus 6x. We subtract, so we're left with 0 and 6x. We divide first term by first term, and that's our constant term. So is this a horizontal asymptote or a slant asymptote? It's a slant asymptote, right? Because it's non-constant. So let's go ahead and draw all of these landmarks. Landmarks being all the intercepts and all that stuff. So we have an x-intercept at -3. We have another x-intercept at -1. Again, we have, we never wrote out the point value, so we know that if it's a y-intercept, it's 0 and then 4.5. So 0, 4.5. We have no holes. We have a vertical asymptote at -2. X equals -2. And we have this slant asymptote at y equals 3x plus 6. So what does that line look like, 3x plus 6? So again, the 6 is our vertical intercept of this line, right? We're trying to graph this line. 6 is our y-intercept. And we have a slope of 3. So when we're graphing a line that has a slope of 3, that means we have rise over run. So 3 is rise and run is 1. So rise over run, we want to we're passing through this point, rise over run, this point, etc. So we know that our graph can't pass this vertical asymptote, and we know that we need to get really, really close to this slant asymptote, and we have to pass through these two intercepts. So this graph is going to look like this on this side. And then on this side, we know that we need to get really, really close to this guy, and really, really close to this guy, and we need to pass through here. So this guy is going to look like this. All right, guys, so that was our first graph of a rational function. There's tons of practice for this on WebAssign. Thanks so much for watching.